So as you can tell, the shielding aspect of ABR Part 3 is very important. It's something that medical physicists must know how to do, and it's something that is often questioned in Part 3. So we have covered this extensively, but to further our discussion, how long is a typical linear accelerator maze? Name some dose contributions that determine maze construction. What is a door comprised of and why? And how would you compute neutron dose at the door? So to begin, a maze is very important in a LINAC room because that will allow you to reduce the particles getting to the neutron door. So not only will this make that door, that maze door, thinner, which this is a very expensive component of LINAC shielding. So the thinner you can make that door, the better. So the longer the maze, the more turns is more beneficial. This obviously it has a lot of factors, but the typical maze is approximately 8 meters. So again, the longer and the more turns is going to reduce the photon and neutron fluence at the door. So I would say approximately 8 meters on this question. Some dose contributions. Now this is important. One thing also to note, any question like this, you want to discuss NCRP 151. Always give a reference regardless of what question you are answering. That just shows that even if you don't know the answer or if you're slightly off, they know that you know where to go. So cite NCRP 151. So first thing we have is scatter. So we have scatter of the primary beam, and then we also have the head leakage. We have the patient scatter. So I'm going to go ahead and put leakage here along with scatter. Then we have for the patient scatter. Now, these are kind of numbers that if you can remember, that's awesome. They're little bonuses, but it really will get you some additional points at your test if you can remember them. So we're looking at 0.5 MeV at 1 meter from the patient. That's approximately what that energy of the particles are once they interact with the patient. Then you have your head leakage, as I mentioned, but not only just from that, but you have the head leakage that is going through the maze wall right here. Then finally, you have neutrons, which are very extremely important, which we will discuss furthermore here. And again, this varies, but the average energy of a neutron is approximately 100 keV at the maze door. So having that number memorized can be important. And then because you have neutrons, you're also going to get neutron capture gammas from the concrete. And I'm just going to put capture gammas here. And so all those go into how you're going to shield the maze and the neutron door. So what is this door comprised of and why? So this is a imperative concept to know. First, you're going to have lead. And so this lead is going to shield the scatter products. It's going to lower the energy of neutron contaminants via the inelastic scattering interactions. You are then going to have BPE. Now, this is called borated polyethylene. Now, this polyethylene thermalizes the neutrons, meaning it reduces the energy of them. And then the boron captures the neutrons, and that does release a gamma. Remember, we talked about neutron capture gammas. It does release a capture gamma of 473 keV. Now, that's important because it releases that, and we need another piece of lead to absorb those capture gammas. Now, this outer layer typically is the thinnest, and just because the capture gammas aren't as energetic as some of the other particles that are first getting to the maze door closest to the maze. So another thing, I guess, to remember too, typically you're going to have a steel casing holding all this stuff together. So from closest to the maze, you're going to have steel, lead, BPE, lead, and then steel. So just that steel casing. And let's talk a little bit about the size of these different pieces. So the steel, typically, we're talking about 0.25 inches, something small. Then we're going to talk about about 3 inches of lead for the first layer. Then about 11 inches of BPE, another 3 inches of lead. Now, this could be less. Typically, obviously, you want to be way more conservative when it comes to these doors and shielding in general. So I think in an exam, say 3 and 3 is going to be a very safe bet. If you actually do the calculations, I think it will be less, but I would just say 3 inches there, and then another 0.25 inches for the steel, which gives us a grand total of about 17.5 inches of door. So that, I don't know if they will go individually, but knowing approximately how thick a door is very important. Now, again, I hate to keep throwing numbers at you, but if you can remember numbers, that will make the examiner feel as though you have a firm grasp of the interactions and what is happening when you are shielding, and then having rough estimates of numbers just shows that you have practical experience, and it just looks a lot better on you as a well-rounded physicist than someone who may not know numbers or kind of just guessing at some of these. So for the TVL, let's talk about the BPE. So for a neutron, TVL in BPE, and now this is for thermalized neutrons, which is what we're going to be getting after this lead piece here. We're looking at 1.2 cm for that TVL. Now, if you are looking at TVLs for a 2 MeV neutron, that obviously is going to be a lot higher because they're not thermalized, they're not slowed down, they're more energetic. That is going to be 3.8 meters. So a lot kind of to learn about the door, but thankfully I feel like it's very intuitive. It makes sense, and you can memorize these and be sure you can definitely spout that out. Finally, how would you compute neutron dose at the door? A very simple answer, Keirsey's formula. And the exam is not long enough for you to do an actual measurement. So maybe know what that equation looks like, reference NCRP early and often, and just don't bog yourself down with details. It's going to have to be simple. If you can just get away with, I would look at NCRP 151, Keirsey's formula. That's how I would calculate it, and that will get you your points. Thanks for watching. If you have any questions, comment below. Best of luck and happy studying.